For as long as we have watched the sky, we believed we understood the sun. It rises, it warms, it burns a constant amid everything that changes. But the truth is far less simple. The sun is not a symbol of stability. It breathes, it cracks, and sometimes it acts in ways that remind us how little we know about the world that keeps us alive. In October of 2025, something extraordinary happened. A vast magnetic wound opened across the surface of the sun, releasing a river of plasma that tore through the void at 700 kilometers per second. At the same time, an object from another star, the interstellar traveler known as 3I Atlas, disappeared behind that same storm of light. When it was supposed to return, it did not. No telescope recorded its reappearance. No trace remained. A visitor from beyond the solar system had entered the sun's domain and vanished. To some, it was coincidence. To others, it was a message, a cosmic alignment too precise to ignore. And while scientists searched for explanations, the event began to grow beyond data or measurement. It became a mirror reflecting something deeply human: our instinct to connect the unconnected, to find meaning in chaos, and to fear the silence that follows an unanswered question. This is the story of that silence of the sun that tore open, of the traveler that vanished, and of what their meeting might reveal about us. Chapter 1. The Solar Event. In the early days of October 2025, a significant solar anomaly was recorded across multiple observatories. The data first appeared as a faint distortion in extreme ultraviolet images, a dark band stretching across the equator of the sun. Within hours, it was confirmed. A massive trans-equatorial coronal hole had opened, linking the northern and southern hemispheres of the solar magnetic field in a single, continuous gap. Through this breach, high-speed solar wind began escaping into interplanetary space, moving at nearly 700 kilometers per second. Coronal holes are not new to science. They appear at intervals, usually near the solar poles, and are a normal part of the sun's magnetic cycle. But this one was different. Its scale and position made it an anomaly, a structure that cut across regions that should have been magnetically closed. The result was a direct, sustained outflow of charged particles aimed toward the inner planets. To observers at NASA's Solar Dynamics Observatory and the European Space Agency's SOHO mission, it looked less like a temporary crack and more like a deep wound, opened by forces still poorly understood. As the images spread through the scientific community, warnings began circulating. The solar wind was expected to reach Earth within 3 days, and geomagnetic storm alerts were issued worldwide. Most experts predicted a strong but manageable event capable of producing intense auroras and minor disruptions to satellites. Still, what made this occurrence notable was not the storm itself, but what happened at precisely the same time, in the same heart of the sky. In another data stream, this time from the Atlas Survey Network in Hawaii, astronomers had been tracking an object of particular interest. Designated 3I Atlas, it was a small, faint interstellar comet, and only the third confirmed visitor from beyond our solar system. Its predecessors, Oumuamua in 2017 and 2I Borisov in 2019, had already transformed our understanding of what drifts between the stars. Atlas, discovered earlier that year, had been following a trajectory that brought it dangerously close to the Sun. As it approached perihelion, the point of nearest contact, its brightness began to fluctuate. Sometimes it surged unexpectedly, as if shedding bursts of material. At other times, it faded until barely visible. The irregular pattern puzzled researchers, but there was little time to analyze it. By early October, the comet's path placed it directly behind the Sun, from Earth's perspective, a region where optical observation becomes impossible. For astronomers, this phase known as solar conjunction is routine. Objects temporarily vanish behind the Sun, only to reappear days or weeks later. That was the expectation for 3I Atlas as well. Observatories around the world prepared for its reemergence on the opposite side of the Sun, estimating late October as the likely date of return. But after the coronal hole formed, something changed. As the solar wind intensified, the comet's projected reappearance never came. No signal, no reflection, no trace. Initially, the absence drew little attention. Tracking interstellar bodies is difficult, and short-term invisibility is common. But as days turned into weeks, the silence became difficult to explain. All optical and infrared surveys reported the same result. Nothing where 3I Atlas should have been. The data line simply ended, leaving a blank interval where a reappearance was expected. A visitor from another star had entered the region of the Sun most active in living memory, and then ceased to exist in observable form. By mid-October, scientists had begun to cross-check archives, looking for indirect evidence. No sudden thermal signature appeared. No fragment trail was visible in SOHO imagery. Even the Parker Solar Probe, which was operating inside the inner heliosphere at the time, recorded no distinct debris plume. It was as though the comet had been erased, not destroyed in a visible explosion, but dissolved so completely that no remnant survived for detection. Then came the solar wind. 3 days after the coronal hole opened, the first wave reached Earth. Geomagnetic monitors spiked. Auroras spread as far south as France, Japan, and the central United States. Commercial satellites briefly lost contact. Aviation networks reported navigation interference. A few regional power grids tripped offline for seconds. It was, by technical standards, a G4-class geomagnetic storm intense, but not catastrophic. Still, the coincidence was impossible to ignore. As the most powerful solar outburst of the year swept past Earth, the only interstellar comet in the inner solar system had vanished without a trace. For the scientific community, correlation does not imply causation. But outside the observatories, the story was already taking shape. Online discussions linked the two events almost immediately, the solar wound and the missing comet, as if the Sun itself had consumed the traveler. Within days, news outlets began repeating the phrase, "The Sun devours an interstellar object," often without context or caution. And while professionals dismissed such headlines, even among researchers, a quiet unease lingered. The timing, they admitted, was remarkable. The most significant solar anomaly of the year had coincided exactly with the disappearance of a rare interstellar body. No one yet called it a mystery, but behind closed doors, data analysts and astrophysicists began asking a question that would dominate the next several months. If 3I Atlas was not destroyed, Where did it go? By the final week of October 2025, the solar storm that had begun with the opening of the coronal hole was still being measured across the heliosphere. Charged particles continued to sweep past Earth, disturbing radio frequencies and low-orbit instrumentation. For scientists, the event was not unprecedented. Solar maximums have produced stronger, yet what drew their attention was the growing silence surrounding 3I Atlas. The comet's predicted trajectory placed it well beyond the solar limb by then. If it had survived, it should have reappeared in wide-field telescopes as a dim, elongated streak near the evening horizon. Instead, the sky remained empty. Search campaigns intensified. The European Southern Observatory, Pan-STARRS 2, and several independent amateurs coordinated nightly sweeps. No reflection, no dust trail. Even the Solar and Heliospheric Observatory, whose instruments routinely capture comets disintegrating near the Sun, recorded no trace. At first, the data were rechecked, then recalibrated, then questioned altogether. Nothing changed. 3I Atlas had simply vanished. The official response from the Minor Planet Center came 2 weeks later. Object 3I Atlas status unknown due to loss of observational contact. A concise statement, almost bureaucratic, but behind it lay an admission that the astronomical record had reached a dead end. The third interstellar object known to humankind had entered the solar environment and failed to exit. Inside research circles, debates formed around competing possibilities. One group proposed thermal disruption, that Atlas nucleus had fragmented as volatile compounds boiled away near the Sun. If true, fine debris would have dispersed quickly, rendered invisible by the brightness of the corona. Another camp considered mechanical fragmentation, suggesting that centrifugal stress or internal voids could have shattered the object into untraceable dust. A smaller minority invoked electromagnetic interaction, arguing that the immense charge differentials within the solar wind might have triggered a rapid electrical discharge, tearing the comet apart at a subatomic level. None of these hypotheses could be proven. The instruments designed to test them had seen nothing. Meanwhile, social media and fringe commentary filled the vacuum. Videos with titles like "The Sun Just Ate an Alien Object" gained millions of views. Forums speculated about government suppression of data, hidden images from NASA, or cosmic warnings timed with Earth's geomagnetic storms. The overlap of genuine scientific silence and public curiosity created the perfect environment for rumor. Each new piece of missing information became confirmation of a larger narrative. In a world used to explanations, the absence of one was interpreted as intent. Back in the data labs, the mood was different, not conspiratorial, but unsettled. Astronomers are accustomed to uncertainty, yet the loss of 3I Atlas was uniquely frustrating. Every prior interstellar object had told a story. Oumuamua's strange acceleration, Borisov's cometary tale. Atlas offered only disappearance. Its trajectory should have taken it out of the inner system and into deep space again, leaving a faint but measurable trace. Instead, the models diverged after perihelion, their predictions scattering like debris. The equations no longer converged on reality. It was as though the object had ceased to participate in the physics that defined it. In early November, new data arrived from the Parker Solar Probe. During its perihelion pass, the probe's magnetometers recorded a localized surge of charged particles, a brief anomaly, lasting less than a minute. It occurred near the same heliocentric longitude where 3I Atlas was last predicted to be. The spike was small, barely above background noise, but in the absence of anything else, it became a focal point. Some analysts dismissed it as a coincidence. Others called it the only trace Atlas left behind. A burst of energy without form, a footprint without a traveler. Outside the laboratories, Earth continued to react to the lingering effects of the solar storm. The upper atmosphere expanded slightly from heating, altering satellite drag. Navigation networks corrected timing errors. At high latitudes, night skies remained tinted green weeks after the main impact. Seismologists noted a cluster of moderate earthquakes, unrelated in mechanism, but uncomfortably synchronous in date. It was enough to sustain public fascination. Every tremor, every aurora, every power fluctuation was now mentioned in the same breath as the missing interstellar comet. News anchors repeated expert reassurances that no causal link existed between solar activity and tectonic events. But the reassurance did little to slow the narrative already forming. The idea that the sun's eruption and the comet's disappearance were two sides of a single event, one that humanity had witnessed but could not explain. By mid-November, the phrase "the vanishing event" began circulating in research memos and discussion boards. It was an informal label coined for convenience, but soon it carried weight. It described not only the disappearance of 3I Atlas, but also the broader realization that observation, for all its precision, could still fail completely. In the modern era of continuous monitoring, the cosmos had reminded humanity that mystery was not yet obsolete. Inside observatories, the search persisted long after the story faded from headlines. Automated surveys continued scanning regions where fragments might have drifted. No signal emerged. Statistically, the case was closed. Yet the scientists involved rarely used the word ended. Instead, they archived the coordinates and left a note for future analysts. Possible unconfirmed reappearance monitor during next solar minimum. The line sat quietly in the database, a placeholder for something that might never return. In retrospect, the event left no physical mark on Earth, no impact, no measurable loss. Yet it shifted the psychological landscape of space science. It reminded researchers how fragile the bridge between observation and understanding could be. A single missing data point was enough to turn knowledge into conjecture. When the sun tore open and a visitor from another star passed behind it, the instruments designed to measure reality blinked. And in that blink, an entire story was lost. The storm subsided in December. Solar activity returned to normal levels, and new events claimed attention. But within a handful of laboratories, the unanswered question persisted, looping quietly in archived notes and late-night discussions. If 3I Atlas was not destroyed by the sun, if it somehow survived the passage unseen, where was it now and what had it become? No one could answer. For the first time in a long while, modern astronomy found itself facing not an absence of technology, but an absence of certainty. The sun had offered a lesson both humbling and vast. Even in an age of constant surveillance, the universe can still withhold the simplest proof that something once observed still exists. Chapter 2: The Interstellar Origin. The story of Three-Eye Atlas begins long before it vanished behind the sun. It starts with a network of telescopes that scan the skies. Every night, the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. Designed to detect asteroids on collision courses with Earth, ATLAS is not meant to hunt for mysteries. Its job is simple: to warn us of rocks that move too fast and come too close. But on a cold morning in early 2025, one of its sensors picked up an object that fit familiar pattern. It appeared as a faint, slow-moving light in the outer reaches of the solar system, just beyond Jupiter's orbit. At first, it was assumed to be an ordinary long-period comet, perhaps one of the many that occasionally drifts inward from the Oort cloud. Yet its motion did not match. Its path curved outward, not inward, a hyperbolic trajectory that no gravitational influence from the sun could contain. When astronomers ran orbital simulations, they all reached the same conclusion. The object was not bound to the sun. It had come from beyond the solar system, and when it left, it would never return. Officially, it became known as Three-Eye Atlas, the third confirmed interstellar object ever detected by humanity. The Three-Eye designation placed it in the same rare category as Oumuamua, the elongated body discovered in 2017, and Two-Eye Borisov, the comet observed in 2019. But while Oumuamua and Borisov had already rewritten the textbooks, Atlas immediately stood apart. Its light curve, the graph of its changing brightness, refused to behave like any normal comet. Where Borisov's activity increased smoothly as it neared the sun, Atlas flickered unpredictably, brightening and dimming without rhythm. Some nights it appeared several magnitudes brighter. Others, it vanished entirely from optical detection. At first, this was attributed to its rotation. Perhaps the comet had an irregular shape or uneven surface, reflecting sunlight like a tumbling mirror. But spectrographic analysis added to the confusion. Unlike typical comets, Three-Eye Atlas showed little evidence of gas emission, almost no water vapor, no strong cyanide bands, and only minimal dust production. If it was shedding material, it was doing so silently. To many researchers, this hinted that the nucleus might be unusually solid, possibly a dense fragment of rock, or conversely, a fragile rubble pile held together by weak gravity. Either way, it did not fit comfortably into any category we knew. The object's velocity relative to the sun was measured at over 30 kilometers per second, too fast for capture, too precise for random drift. It was moving along a path inclined by about 40 degrees to the ecliptic, the plane of the planets, suggesting it came from a region of space unconnected to our stellar neighborhood. For comparison, Oumuamua had approached from the direction of the constellation Lyra, and Borisov from Cassiopeia. Atlas seemed to arrive from somewhere between the constellations Aquila and Ophiuchus, a patch of sky with no known nearby systems capable of ejecting large bodies our way. That absence of origin led to new questions. How do interstellar objects like this reach us at all? The leading theory is that during the early formation of planetary systems, gravitational interactions can fling debris outward at immense speeds, turning them into cosmic exiles. Most would drift unseen in the vast emptiness between stars. Statistically, only a fraction ever pass close enough to be illuminated by our sun. For humanity to have observed 3 in less than a decade was not only extraordinary, it was improbable. Some researchers suggested that this might mean our detection technologies were improving faster than expected. Others quietly wondered whether something unusual was increasing the traffic of interstellar debris through our region of space. As the months went by, 3I Atlas grew brighter. Its apparent magnitude increased faster than predicted, implying either that it was larger than initial estimates or that it was fragmenting. Images from the Hubble Space Telescope hinted at subtle elongation, a stretched coma, as if the nucleus were shedding faint material along its orbital line. The pattern resembled what astronomers call progressive structural failure, when internal stresses begin to tear a comet apart as it heats unevenly. If true, Atlas might have already been disintegrating even before reaching perihelion. Still, despite its instability, the object attracted attention not only from astronomers, but from the general public. It was the first interstellar visitor to be tracked in real time, and the media quickly labeled it the Ghost Comet. Some called it a relic of another star. Others, more romantically, imagined it as a messenger from elsewhere, a physical memory of a distant system, crossing our sky for the briefest moment before vanishing forever. By mid-2020, telescopes across both hemispheres were pointed toward its faint trail. Every data point, every brightness fluctuation was recorded and compared. Scientists hoped to capture a full profile of composition before the comet disappeared behind the sun later that year. In technical reports, it was described as scientifically invaluable. To the public, it was something else, a reminder that the solar system is not an island. The space between stars is not empty. It is filled with travelers like this, ancient and silent, moving through our neighborhood before continuing into the dark. As autumn approached, the orbit of 3I Atlas carried it inward, accelerating under the pull of the sun. Its trajectory was precise, its coordinates predictable until the data began to drift. Minor deviations appeared, then widened. Even accounting for solar radiation pressure and outgassing effects, the math refused to close. Somewhere between observation and projection, the object was no longer where it should have been. To some researchers, it was a computational glitch. To others, it was the first sign that something about 3I Atlas defied the models built to understand it. It would not be long before that uncertainty became a mystery and a warning of how fragile even our best predictions could be. In scientific terms, 3I Atlas was a visitor without a home. Its hyperbolic orbit confirmed that it did not belong to the sun, nor to any gravitational family within the solar system. Every known planet, moon, and asteroid follows an elliptical path, bound to the star by invisible lines of motion. Atlas did not. Its eccentricity was greater than one, a mathematical way of saying it came from elsewhere and would never return. For the scientists who studied it, this was both thrilling and humbling. We were observing a fragment of another system, a piece of alien history passing through our own. Attempts to trace its origin began as soon as its trajectory was confirmed. By working backward through its path, Researchers at the Center for Near-Earth Object Studies projected its point of entry into the solar system, a direction near the constellation Aquila, crossing the galactic plane at a steep incline. No known star in that region could account for its ejection. Even if it had once orbited a distant sun, that parent star had long since drifted far from the point of intersection. Statistically, the trail led to interstellar space, a region with no fixed origin, only a record of velocity and angle. In essence, Atlas could have come from anywhere. What made this realization more intriguing was its timing. Oumuamua, the first interstellar object ever found, had entered our system less than a decade earlier. Before 2017, humanity had never confirmed the passage of a single body from beyond our sun. Now, within just a few years, 3 had appeared. For a universe that measures its events in billions of years, such repetition was remarkable. To many astronomers, it hinted that our region of space might lie near a drift corridor, a galactic pathway, where debris from other systems occasionally passes through. To others, it was simply a matter of improved detection technology, better telescopes, faster surveys, and more sensitive algorithms. Still, the coincidence was difficult to dismiss entirely. Cometary dynamics in interstellar space are poorly understood. Without the stabilizing influence of a nearby star, small objects travel under the combined pull of galactic tides, molecular clouds, and ancient collisions. Some drift for eons, untouched. Others are accelerated by encounters with giant planets in their original systems, hurled outward at escape velocity. If 3I Atlas followed such a fate, it might have been expelled hundreds of millions of years ago. An orphaned remnant from the early chaos of planet formation, wandering through the dark until gravity pulled it into the sun's reach. Spectral data supported that possibility. Although weak, readings taken before the comet's disappearance revealed traces of magnesium and silicate common in rocky asteroids, but rare in active comets. The ratio between dust and gas emissions was abnormally low, suggesting either that volatile materials had already been stripped away by radiation during its long interstellar journey, or that the nucleus was composed of denser, less reactive material. In either case, it was ancient, older than our solar system itself, likely formed in a different molecular cloud altogether. That realization reframed the discussion. If Atlas truly came from beyond, then each particle within it carried a chemical memory of another star. To study it was to study another world's building blocks. For planetary scientists, this was the closest humanity had ever come to touching interstellar matter directly. And that made its loss behind the sun all the more frustrating. An object that could have revealed the history of a distant system had instead disappeared at the moment of greatest visibility. Still, the data we do have reveal much about its behavior. Interstellar comets, like Atlas, experience forces that ordinary models cannot fully predict. They travel at high relative velocities and encounter solar radiation without magnetic adaptation. In simple terms, they have no shield, no evolved structure for surviving a star's environment. The result is an extreme response: rapid ionization, asymmetric outgassing, and unstable rotation. Some researchers compared it to a spacecraft tumbling through a furnace, heating unevenly until its structure fails. In that sense, 3I Atlas' irregular light curve, its unpredictable flashes and fades, may not have been random at all, but the visible signature of structural breakdown. Such an interpretation aligns with later comparisons to known sun-grazing comets. Objects like Comet ISON in 2013 and Lovejoy in 2011 disintegrated under solar heating, despite being native to our system. Atlas, lacking even the minimal cohesion of those bodies, may have begun fragmenting long before reaching perihelion. If so, the disappearance observed later, in October 2025, was not a sudden event, but the final stage of a slow and inevitable collapse. The fragments, scattered across a wide arc behind the sun, would have been too small and too faint to detect from Earth. Still, not everyone agreed with this explanation. A few astrophysicists argued that 3I Atlas deviations in trajectory could not be fully explained by outgassing alone. The magnitude of its non-gravitational acceleration seemed disproportionate to its observed mass. This discrepancy echoed earlier debates around Oumuamua, whose unexpected speed change led some to propose unconventional causes from hydrogen outflow to, in extreme interpretations, artificial origin. No one suggested that Atlas was anything similar, yet its anomalies revived the same unease. Our models could describe what happened, but not by late 2025, when the comet failed to reappear. The effort to understand its composition became a matter of reconstruction. Archived data, spectral lines, and orbital simulations were reprocessed repeatedly, each time yielding slightly different answers. Some analyses proposed that the nucleus was compact and metallic. Others favored a fragile aggregate of silicate dust. Even the estimated size varied widely, between 200 meters and 1 kilometer in diameter, depending on assumed albedo. Every dataset raised new uncertainty, as though the object itself resisted being defined. For the public, such ambiguity was frustrating, but for science, it was a reminder that discovery often begins in confusion. 3I Atlas had entered our awareness carrying questions we were not yet equipped to answer. Its origin lay somewhere beyond the visible sky, its structure beyond clear classification. And when it vanished, it left behind not just an empty patch of space, but a trail of contradictions, clues pointing in every direction at once. To some, that was the essence of exploration. We search the unknown not to find certainty, but to learn what we do not yet understand. 3I Atlas offered that lesson the hard way, by slipping beyond reach just as we began to see what it was. Chapter 3: Collision of forces. When an interstellar object crosses into the inner solar system, it enters a domain shaped entirely by the sun. Here, gravity is not the only force that matters. The sun emits a constant stream of charged particles, protons, electrons, and ions, known as the solar wind. Invisible yet relentless, it carries magnetic fields that twist and ripple through space, shaping a vast bubble called the heliosphere. Every planet, every comet, and every grain of dust inside this region lives within its influence. For most comets, this encounter is survivable. They are native to the sun's radiation, formed with volatile materials that respond in predictable ways. But 3I Atlas was not from here. It had never experienced this kind of energy before. It arrived without a magnetosphere, without a stable coma, and with a structure likely weakened by eons of radiation exposure. When such an object meets the solar environment, it doesn't just heat, it transforms. At its closest approach, Atlas would have faced a radiation flux hundreds of times stronger than anything it encountered in interstellar space. The solar wind at that distance travels near 700 kilometers per second, carrying both plasma and magnetic turbulence. For comparison, that's equivalent to a continuous storm of atomic particles striking every square centimeter of the comet's surface with the energy of a high-speed bullet, not once, but constantly. The fragile outer layers of dust and ice would sublimate instantly, leaving the denser core exposed to rapid ionization. Under those conditions, electrostatic charging becomes inevitable. As electrons are stripped away from the surface, the nucleus begins to build a potential difference relative to its surroundings. Normally, comets discharge this buildup through jets of gas and dust, the glowing tails we see in telescopic images. But Atlas, according to early spectrographic data, had little volatile material to vent. Without that release mechanism, electric stress could accumulate until the surface literally ruptured. This is the foundation of what some call the electric comet model. The idea that plasma interactions, not just heat, can fragment a comet from within. Traditional astrophysics remains cautious toward that hypothesis. The standard explanation still relies on thermal fracturing when solar heating causes trapped gases to expand and crack the nucleus. However, for an interstellar object like Atlas, the two processes might not be mutually exclusive. If the nucleus was already porous, filled with microcavities from ancient impacts, both heat and charge could have acted together. As the sun's magnetic field fluctuated, alternating currents of plasma may have induced localized explosions, small but cumulative, destabilizing the structure over time. Data from previous sun-grazing comets offer useful comparisons. In 2013, Comet Ison broke apart after passing within 1 million kilometers of the Sun. In 2011, Comet Lovejoy survived its perihelion, but emerged severely fragmented. Both were far larger than Atlas, and both were native to our solar system. Yet they failed to endure. For an interstellar visitor smaller, older, and more fragile, the outcome was almost predetermined. As Atlas approached the Sun, the solar wind was unusually turbulent. Magnetograms recorded strong variations across the equatorial region, the same region where the trans-equatorial coronal hole later formed. It was a chaotic environment, open magnetic field lines whipping out into space, plasma density fluctuating wildly. Within that storm, any object without a protective magnetic boundary would be exposed directly to electrical currents measured in millions of amperes. If Atlas entered that zone at the wrong moment, the result could have been catastrophic, a rapid ionization event that tore it apart before it reached perihelion. Yet no direct observation captured such a moment. If fragmentation occurred, it did so unseen, hidden behind the sun's brilliance. By the time the coronal hole opened days later, nothing remained large enough to reflect sunlight. The comet's disappearance was not the result of a single explosion, but of progressive disintegration, the slow erasure of matter by a field it was never built to survive. Even without visual confirmation, the physics suggest this scenario fits the data. Simulations run afterward by solar researchers modeled what would happen if a low-mass, high-porosity body entered a region of enhanced magnetic turbulence. In nearly every case, the result was total loss fragmentation down to micron-sized dust, dispersed and carried away by the solar wind. Such dust would be indistinguishable from the background plasma flow, effectively invisible to observation. That invisibility explains the blank data stream recorded by SOHO in stereo. There was nothing large left to detect. Still, one aspect remained unresolved: the timing. If Atlas disintegrated before the coronal hole opened, then the two events were separate. If the breakup occurred during the solar eruption, it could imply direct interaction. The chronological overlap was exact enough to keep the question alive. Astronomers couldn't confirm a causal link, but they couldn't dismiss it either. Even within the cautious language of peer-reviewed reports, words like correlated and coincident began to appear, careful terms that hint at curiosity restrained by skepticism. For the public, the notion of a collision of forces was irresistible. A storm from our sun meeting a traveler from another star. Two energies from opposite origins colliding in silence. Science could not dramatize it that way, but the idea carried its own symbolic weight. It reminded observers that the solar system is not a closed space. The boundaries of the sun's influence are porous. Interstellar matter crosses them more often than we once believed. And when it does, the encounter is not gentle. It is an exchange measured in plasma, heat, and destruction. By late 2025, models of Atlas path were archived, and attention shifted to new data. The comet had ceased to exist as an object, but not as a question. Its fate illustrated a deeper principle of astrophysics, that the space between stars is not empty, but filled with debris still bearing the fingerprints of other suns. When that debris meets our star, the result is not always illumination sometimes. It is obliteration. When the data finally stopped coming in, the question that remained was simple but unanswerable. What exactly happened to 3I Atlas inside the solar environment? The lack of observation left scientists to reconstruct the event from models, fragments of telemetry, and comparison with previous sun-grazing comets. From that effort emerged three leading hypotheses, each plausible, none complete. The first and most widely accepted is the thermal breakdown model. In this view, the intense radiation near the sun caused rapid sublimation of surface materials, leading to uneven expansion within the nucleus. The process is similar to what happens when ice cracks under sudden heat, but on a cosmic scale. As internal pressure builds, microfractures multiply until the structure fails catastrophically. For comets composed of loosely bound rubble, as many are the result is total disintegration. Simulation data suggests that, at temperatures exceeding 1000 Kelvin, even silicate-rich aggregates can crumble when stress gradients exceed a few kilopascals. If 3I Atlas was already weakened by prior fragmentation, thermal collapse could have been inevitable. This explanation is consistent with what we know from Comet Ison and other sun grazers that disintegrated near the sun. Yet, thermal models alone fail to explain every anomaly. In the case of Atlas, no sudden brightening was recorded, no flash of vaporization, no plume detectable by SOHO. Typically, a disintegrating comet releases a burst of dust that scatters sunlight, creating a short-lived surge in luminosity. The absence of such a signal suggested that the material might have been stripped away more gradually, or that the fragments were too fine to reflect light efficiently. Alternatively, the breakup may have occurred behind the sun, hidden from all Earth-based view. Either possibility leaves the same conclusion. The comet ceased to exist, but its death went unseen. The second hypothesis, less conventional, but increasingly considered, involves plasma discharge events. The sun's environment is not merely hot, it is electrically active. As streams of charged particles interact with objects lacking magnetic shielding, they induce potential differences that can exceed millions of volts. Laboratory experiments with dust aggregates under simulated solar wind conditions show that surface potentials can trigger micro-arcing, tiny electrical discharges capable of ejecting material from the surface. If such processes occurred on a large scale around Atlas, the result could have been an internal explosion not caused by heat, but by charge imbalance. Proponents of this theory point to the timing. The coronal hole that opened in early October would have amplified solar wind density and magnetic turbulence, creating ideal conditions for electrical interaction. In that scenario, Atlas did not melt. It was electrically eroded. Skeptics of the plasma model argue that while small-scale discharges are possible, the energy required for total destruction would be enormous. Moreover, no direct measurement confirms that such potentials can accumulate in a natural setting without triggering earlier discharge. Still, the model remains intriguing because it aligns with one unignorable fact: the event's correlation with an unusually strong solar wind. Even if plasma did not destroy the comet outright, it may have accelerated the fragmentation initiated by heat and stress. In the turbulent region near the coronal hole, the boundary between thermal and electrical processes blurs. The comet was likely caught in both a physical and electromagnetic crucible. A third line of thought focuses on radiation-induced collapse. Here, the culprit is not heat or electricity, but molecular breakdown from high-energy particles and ultraviolet flux. Over millennia of interstellar exposure, cosmic rays would have altered the chemistry of Atlas' surface, creating a brittle crust rich in complex carbon compounds. When bombarded by solar radiation, these materials can decompose violently, releasing trapped gases and weakening structural bonds. Essentially, the comet could have been destroyed by its own history, a delayed chemical detonation written into its composition. This theory fits with spectral hints of organics found in early observations, but the data are too limited for confirmation. Each hypothesis addresses part of the mystery. None accounts for all of it, and so the scientific record remains divided. Thermal breakdown explains the mechanical failure. Plasma discharge explains the timing and correlation with solar activity. Radiation collapse explains the absence of volatile emissions. Together, they form a mosaic of partial truths, fragments of understanding mirroring the fragments of the object itself. By November 2025, the analysis had shifted from physical models to reflection. The disappearance of 3I Atlas had become more than an astronomical curiosity. It was a test of how much we truly understand the space near our own star. For centuries, humanity viewed comets as simple wanderers, their behavior governed by gravity and heat. Atlas challenged that simplicity. It reminded scientists that the sun's realm is not a passive stage, but a dynamic system where gravity, plasma, magnetism, and chemistry all compete. Every object that enters must negotiate with forces beyond human replication, a collision of physics both known and not yet known. Inside the data archives, the final entries for 3I Atlas remain clinical. Coordinates, signal loss, null detection, no final image, no closing frame, only silence. But behind those sterile lines lies a story of extremes. An object older than the sun, traveling for millions of years, undone in a moment by the forces that define our star. Some researchers describe it as destruction. Others, more philosophically, suggest transformation, the conversion of matter into plasma, scattered through the heliosphere, absorbed into the same wind that erased it. In that sense, Atlas did not vanish. It became part of the sun's breath, diffused into the energy that sustains the solar system itself. Was that the end? Or simply a change of state? Science offers no certain answer. But the event leaves a quiet reminder. Between stars, the boundary between creation and annihilation is often the same line crossed silently, without witness, and measured only by the questions it leaves behind. Chapter 4. The Vigil. In the weeks that followed the solar event, the night sky became an object of quiet expectation. Every major observatory across the globe turned its instruments toward the region of the sun, where 3I Atlas was predicted to emerge. The calculations were precise. If the comet had survived perihelion, it should have reappeared in the western twilight of late October, faint but visible as a small streak of reflected sunlight. Nothing appeared. At first, few were alarmed. Temporary losses are common during solar conjunction. Even the most stable orbits can drift slightly under radiation pressure, causing brief deviations in expected position. But as days turned to weeks and every scan returned the same empty frame, patience began to erode. The third interstellar visitor ever detected an object that had crossed billions of kilometers of space, had vanished less than 50 million kilometers from Earth. The effort to recover it became a global collaboration. From the ground, telescopes in Chile, Spain, and Hawaii conducted nightly sweeps using wide-field CCD arrays. In orbit, the Solar and Heliospheric Observatory, SOHO and Stereo, monitored from different vantage points, hoping to catch any glint of reflected light from dust or fragments. NASA's Parker solar probe, moving deep within the inner heliosphere, continued to transmit data on local plasma conditions. Even amateur astronomers joined the search, feeding their findings into a shared online network maintained by the Minor Planet Center. Each morning, new files were uploaded. Each night, the results were the same. No detection. Inside professional circles, the mood was a mix of curiosity and frustration. The silence of the sky is not unusual, but the precision of the predictions made the absence impossible to ignore. In astronomy, nothing disappears completely. It either changes form or falls beyond sensitivity thresholds. For 3I Atlas, to remain undetected across all instruments suggested one of two things: total disintegration or an extreme drop in brightness, perhaps by a factor of thousands. Either outcome was remarkable. By early November 2020, reports from the European Space Agency summarized the situation plainly. The predicted coordinates yield no optical source, no infrared or reflected light above background levels detected. It was the kind of language designed to sound routine. But between the lines, the message was clear. If Atlas had survived, it was now effectively invisible. Within the astrophysics community, attention turned toward indirect evidence. Researchers analyzed solar wind density and magnetic field variations, looking for traces of material that might have been released during the comet's passage. Tiny fluctuations in particle composition, increases in dust, or ionized silicon were noted by the Parker Solar Probe. They were small, statistically uncertain, but intriguing. Some scientists argued that these were remnants of Atlas, absorbed and diffused into the solar stream. Others warned that the signal was too faint to distinguish from normal solar variability. The debate lingered in conference calls and email threads, unresolved but quietly persistent. Meanwhile, outside the professional sphere, the story had taken on a life of its own. Media outlets revisited the timeline, juxtaposing images of the coronal hole with computer renderings of Atlas. Headlines spoke of the comet that entered the sun, or the star visitor that never returned. Public interest surged briefly, then faded, replaced by newer stories. For the scientists still watching, however, the mystery remained deeply personal. Months of observation, hundreds of hours of data, and the conclusion was absence. In mid-November, the International Astronomical Union, IAU, convened a small workshop to review the event. It was held remotely, connecting observatories from 5 continents. The tone was cautious, but the underlying sentiment was shared. This was not an ordinary loss. One senior researcher remarked, "It's as if we followed a signal into the sun, and it stopped answering." The phrase resonated. It captured what numbers could not, the quiet dissonance between expectation and reality. Attempts were made to rerun the trajectory using alternative gravitational models. Some hoped that outgassing before perihelion might have shifted the orbit enough to move Atlas outside predicted coordinates. Yet, no combination of parameters produced a path that matched the lack of visibility. Either the comet had fragmented entirely into dust smaller than 1 micron, or it had entered a state of complete dormancy, a dark, inert rock indistinguishable from the background of the solar wind. Chapter 5. The Interpretations. When the instruments stopped recording, and the last coordinates of 3I Atlas faded from the tracking maps, what remained was not data but silence, and silence, by nature, demands interpretation. It is a reflex older than science itself. Where evidence ends, imagination begins. And in the absence of an image, humanity created one. Within weeks of the comet's disappearance, 3 parallel conversations unfolded, one in the scientific community, one in the public sphere, and one in the quiet space between them. Each sought to explain the same event, yet each spoke in a different language. 1. The scientific response. Inside research institutions, the tone was restrained. Teams at NASA, ESA, and the Max Planck Institute began assembling post-mortem analyses, reports that transformed speculation into structured hypotheses. Phrases like non-detection, consistent with disintegration and possible correlation with solar activity, became the grammar of closure. Yet even in these formal documents, there was a subtle acknowledgement of wonder. To study 3I Atlas was to touch the boundary between two domains, the measurable and the unknowable. And while science thrives on measurement, it is also haunted by what cannot be measured. One astrophysicist described the experience as watching a message written in plasma that erased itself before we could read it. Another noted, the most extraordinary event in recent solar observation ended not with a signal, but with an absence. It wasn't disappointment so much as reverence, the sense that something significant had occurred just beyond the reach of verification. The data analysts who had spent months tracking Atlas often spoke of it as though it were alive, a traveler, a visitor, a silent interlocutor. That language was metaphor, of course, but it revealed something deeper about the human side of science. The need to personalize the unknown, to name it, to grieve when it vanishes. For all its rigor, astronomy remains a form of storytelling, one told through numbers, light curves, and coordinates, yet guided by the same instinct that once turned constellations into myths. Outside the laboratories, the story of 3I Atlas took a different form. The internet had followed the event in real time, videos showing simulation arcs, comment sections speculating about alien technology, and documentaries narrating the final dive into the sun. It was the perfect storm of imagery, an interstellar object disappearing behind our star, timed precisely with a massive solar eruption. The narrative wrote itself. Within days, forums filled with theories. Some claimed Atlas was artificial, a probe sent by a distant civilization and intentionally destroyed upon mission completion. Others suggested it had been harvested by the sun, absorbed as energy in a cosmic exchange. A few interpreted it through ancient symbology, the return of fire to its origin, the merging of the foreign and the divine. In each case, the science became the canvas on which belief painted its own version of meaning. For many, these speculations were not expressions of ignorance, but of hunger, a search for coherence in a universe that often refuses to provide it. The disappearance of Atlas was not frightening because it was unknown, but because it was unexplained. And in a digital world conditioned to expect resolution, mystery itself became an anomaly. To say we don't know felt almost transgressive. 3. The cultural mirror. Between the scientists' restraint and the public's imagination lay a third realm, the cultural reflection. Writers, philosophers, and even theologians began referencing the event as metaphor. Editorials appeared with titles like When the Cosmos Goes Silent and The Vanishing, that defined a generation of observation. Podcasts compared it to the disappearance of Amelia Earhart, Voyager's fading signal, or the last transmission of deep space probes. It became part of a growing narrative about human limitation, how every step outward reveals more we cannot reach. Some saw Atlas as a symbol of fragility, that even across interstellar distances, endurance is finite. Others saw connection, that the matter of distant suns still returns, completing a cycle of cosmic exchange. In lectures and essays, scholars of science communication noted that Atlas had achieved what few astronomical events could. It had reminded people that mystery still exists in an age of total surveillance. Yet, amid all these interpretations, one theme remained constant: silence as substance. It was not a failure of observation, but a result of the universe operating on its own terms. In that sense, 3YI Atlas was neither a warning nor a miracle. It was a demonstration that nature does not owe us visibility, and that meaning is often found not in the data we collect, but in the space left when the data runs out. 4. The line between evidence and meaning. By early 2026, conferences began including sessions not on the physics of Atlas, but on its cultural footprint. Researchers debated whether the story had been distorted by media dramatization or enriched by public curiosity. Some argued that the blending of fact and speculation was dangerous, feeding pseudoscience. Others countered that curiosity, even messy, emotional curiosity, is still the root of exploration. One speaker summarized the dilemma succinctly: when science stops at no detection, people will write the rest of the sentence themselves. It was not criticism, but observation. Science builds fences around what can be proven. Imagination crosses them to see what might lie beyond. Between those two movements, the cautious and the curious progress happens. 3I Atlas became a case study, not only in astrophysics, but in epistemology, how we know what we know, and how we behave when we cannot know more. By the time the event faded from headlines, its traces had already scattered in academic papers, in online speculation, in quiet personal awe. The comet itself was gone, but its absence had created a new presence, a reminder that every discovery ends where interpretation begins. Whether through equations or myths, data or dreams, we continue the same work to draw meaning from the silence between stars. As months passed and the event of 3Y Atlas receded into the archives, the world's attention moved on, but the silence it left behind endured. Somewhere in that absence, something changed. It wasn't a discovery or a theory, but a shift in how we think about the unknown. The disappearance of an interstellar visitor had reminded humanity of an uncomfortable truth: that not every question leads to an answer. Among astronomers, the event became a quiet reference point, an anecdote shared between data sessions, a reminder of humility. The lesson was simple but profound. Even with all our instruments, our models, and our predictive algorithms, the universe retains the right to surprise us. The loss of Atlas was not a failure of observation, but proof of how observation itself has limits. In every field of science, there comes a moment when measurement reaches its horizon, and beyond that, there is only inference, faith, and wonder. In early 2026, a small paper appeared in the Astrophysical Journal Letters. It contained no new data, only an analysis of probabilities, the likelihood that 3Y Atlas had survived, fragmented, or vaporized. The conclusion was mathematically precise and emotionally neutral. The object known as 3I Atlas most likely ceased to exist as a coherent body during Helian passage. No dramatic phrasing, no lingering metaphor. Yet behind those few sterile words lay the entire weight of human curiosity. A journey across billions of kilometers, ending not with an image, but a sentence. And still, some part of the story resisted closure. Even now, long after the reports were filed, telescopes continue to scan the region around the sun each year during the same week in October, just in case. Not because the scientists expect to find anything, but because the act of looking itself has meaning. The vigil continues quietly, without announcement. It is not about confirmation anymore. It is about remembrance. In classrooms, professors now use Atlas as a case study, not of astrophysics, but of human perspective. They ask students to consider why we care so deeply about what vanishes, why a comet, barely visible for a few weeks, could evoke such lasting emotion. The answers vary. Some speak of mystery, others of connection. But all point toward the same instinct, the need to find ourselves reflected somewhere beyond Earth, even in the brief arc of a foreign fragment crossing our sky. There's something uniquely human in the way we respond to silence. We fill it with meaning. We name it, narrate it, turn it into myth. Our ancestors once looked at comets and saw omens. We look at them now and see data, yet the feeling deep down has not changed. A streak of light across the dark remains both a question and an answer. 3. Atlas became that for a new generation. A story of contact without communication, of evidence without conclusion. In philosophical circles, the event has taken on a symbolic role. Some call it the mirror comet, an encounter that reflected not another civilization, but ourselves. We looked outward and saw our own limits staring back. We imagined something grand, perhaps intelligent, visiting us from the deep. Instead, we witnessed an object obeying the same indifferent physics as everything else and found awe in that indifference. It was not a message, but it made us listen. Theologians have written about the event too, calling it a reminder that creation and destruction are not opposites, but continuations of the same process. In their view, Atlas did not die. It simply returned to the medium from which it came. Its atoms are now part of the solar wind, scattered across magnetic fields, drifting through the same particles that touch our atmosphere every day. If one could trace them, those atoms might now be falling across the poles as aurora's faint echoes of a journey that ended in light. Back in the data centers, the archived folder labeled 3I Atlas Final remains untouched. Inside are lines of numbers, coordinates, timestamps, spectral ratios, all that's left of the third interstellar visitor we ever met. If you open it, there's no image, no sound, just patterns of digits arranged in neat, silent order. But to those who remember watching the live feeds, that emptiness still carries weight. They remember the anticipation, the brief hope that maybe, just maybe, this visitor would tell us something new about where we come from. Instead, it told us something else. That we are still learning to listen to the universe when it says nothing at all. For a few brief weeks, a rock from another star crossed our sun, and for that moment humanity watched together. Then it was gone. Not with fire or noise, but with quiet precision, leaving us only with questions. And perhaps that is enough. Because sometimes the value of discovery is not in what it reveals, but in what it makes us seek. In the end, every era of exploration begins the same way, with a silence that demands interpretation. 3 Atlas was one such silence, vast, indifferent, yet profoundly human in its aftermath. Its story reminds us that the universe is not obligated to be understood, only witnessed. And in witnessing it, we discover something about ourselves, that even in absence we reach out, that even in darkness we imagine light, and that even when the cosmos says nothing, we still find meaning in the quiet that follows. 3 Atlas, a name that will fade from the data logs, yet remain in memory, in curiosity, in the unspoken awe of a question without an answer. For in the silence between the stars, perhaps the greatest story is not what we find, but what we still seek.